Well, it's great to be with you. Thanks ever so much for the opportunity to come and share with you what I've learned over the years about flight. As I indicated, I've always had an interest in flight. This is an Arctic tern on its way from the North Pole to the South Pole, at which they make a trip every year without any difficulty. The only thing that stops them is birds of prey, usually in the Mediterranean area, where they dive bomb, sadly, onto these hardly unsuspecting because they know they're going to be preyed on, but they can't always avoid the peregrine falcons and the others travelling at much greater speeds and grabbing these Arctic terns out of the sky. But an amazing feat, though, of aerodynamics, because these birds fly 12,000 miles from one pole to the other. There's another beautiful view. There's a really tremendous photograph there of Arctic terns. So I'm going to talk to you a little bit about the wonders of flight. This is sort of the wow factor. And then I'm going to get a little bit more detailed, because I know you're scientists here and I know you'll be saying, oh, well, that's nice, that's beautiful, but I really want to get into the science of it. Well, I think you shouldn't forget, though, we shouldn't despise just the wonder of the world. And I don't actually say that it's wrong to just sit back and think and just and look at the entirety of the particular creature that you're studying. You can sometimes get so close to the science that you forget to see things holistically. And when you do see the wonder of what is, I would suggest to you, created, that's my position, as you obviously know, then you begin to see the enormity of what's involved in the alternative, which is to say that this creature has evolved over many years. The wonders of flight, let's now just consider some details. The migration, I've just mentioned to you, the Arctic terns, which fly a huge distance from one pole to the other. Somebody once asked, why do birds fly south in winter? And you know what the answer was?
Too far to walk.
Exactly, you preempted me, sir. Too far to walk. Well, you meant to laugh there, but you don't have to if you don't want to. But there we go. Let's talk about another one, though, which this time the Arctic tern, of course, stops on the way. It makes a huge trip, one pole to the other, but this next one is the Pacific golden plover, which migrates between northern Canada and Alaska and Hawaii, a distance of about 3,000 miles, and the young make the journey after the adults, and they go alone. That's the most amazing thing about the Pacific golden plover. So that journey is a long distance. It actually takes 5 to 6 hours if you fly from Los Angeles to Honolulu, and if you're flying in one of our jets that we have today, Boeing 777 or whatever. So it's actually a large distance. And if you know anything about the islands of Hawaii, if you're a pilot, they are just little dots in the middle of a massive ocean. In other words, there's no real landmarks until you're within about 50 miles, maybe 20 miles, somewhere in that region, you begin to see it over the horizon. If you're flying at the sort of heights that these birds would fly at, it would be a much closer distance. So there is no way you've got cues on the way to tell you how to get there, all right? So the Pacific golden plover, you realise, flies this distance without any stops. So it's got to make a 3,000-mile trip. And the point that I'm making here, of course, is that the Pacific golden plover young ones have never made the journey before. So they can't say, oh, well, they did this in the past, and they were guided by mother and dad, and they knew the way to get there. They actually are born having never been there before, and they then make the journey after their parents have already gone. There is a lot involved, actually, in making a trip. Anybody who's a pilot or is interested in piloting knows that you've got to work out your weight to make sure that you can take off all right, and to make sure that you've got enough fuel on board in order to make that trip. If you take too much weight, you'll go down into the sea. If you don't take enough, you'll go down to the sea as well. You're between a rock and a hard place, as it were. because either you haven't got enough fuel, or else you've got too much fuel, you make the weight too great, so you use too much energy to get there, etc. So these calculations are quite important. Now, I don't think a young Pacific golden plover goes through all the innuendos of all the maths, but you can look at it in the book. In the Beginning Was Information. All the details of that calculation are there. The book by Werner Gitt, where he goes into this in some detail. How do birds do it? Well, we know that they've got cues. People have recently found magnetite in their brains. So the cue of the magnetism of the Earth is believed to guide these birds. The sun also, and its direction will give them some indication. But the other point is, how do they know, even if they have got these cues for the north, south, east and west, how do they actually know where Hawaii is? Even if they got these cues, it still doesn't explain how do they know where to go on the map that they may have in their brains by instinct. It's really quite a remarkable point, and nobody knows. That answer has not yet really been established. A modern cockpit must use sophisticated equipment to keep track of position. These birds do it possibly by magnetisms, possibly by other cues. But as I've just said, they still need to know where Hawaii is. Well, this bird takes the biscuit. This is a different bird. This bird also flies non-stop, this time across the whole of the Pacific. And it doesn't do it the easy way, which would be to go sort of gently southwest from the coast of the USA to New Zealand. Oh, no. It goes right from Alaska, Anchorage way, and it flies all the way down to New Zealand, 7,700 miles. Not the BBC, the Daily Telegraph some years ago, 3 years ago, had a little article on this with a website. I'm not sure whether it's still there, but they'd actually tracked this bird, and it's the godwit, and it travels right across the Pacific, and it takes 6 days to do it, and it travels non-stop. Quite amazing. So there are some amazing feats of migration. As I've said, it's probably by seeing the Earth's magnetic field. You've got large distances involved. You've got to get a correct payload of fuel, which of course for a bird is not hydrocarbons. It's by eating fat, which it takes from its body as it's flying. There is no training, as I indicated, with some of these birds, particularly the Pacific golden plover. How about speed? The wonders of flight. Now, not migration, but speed. Swifts, did you know that they feed and sleep on the wing? It's not quite true that they sleep entirely. What they do is they shut down one half of their brain, while the other half is just sort of keeping going in the flight towards wherever their destination is. And they fly at night at about 10,000 feet, which is very high for a bird. If you were to fly at 10,000 feet, you'd struggle because of the oxygen content of the air changing. But they manage okay. They keep direction, these birds, not by magnetism. They don't keep direction by the sun, which is down. The stars, they don't do it by that either. They actually keep their direction, it has been proved, by setting it to begin with and then taking account of the forces of the wind. In other words, they have such sensitivity to the aerodynamic forces in your sideways that they're able to correct for it automatically. That's how swifts operate. And they sleep and eat on the wing during the day, like martins and other birds, similar family of birds. They will feed on insects all the time. It's really quite remarkable. Sometimes they'll come a bit lower, obviously, than the 10,000 feet. They will come lower to pick up the appropriate insects. Swifts have greater agility than modern military aircraft. The only exception really for birds is that they've never gone supersonic. But other than that, when people say, well, you know, we've gone one better, well, only in the area of supersonic flight. The world's record for speed amongst living things is actually the Indian spine-tailed swift, a bird which was repeatedly clocked in level flight over a carefully measured 2-mile course in as little as 32.8 seconds, which means that it was going at 219 miles an hour, which, although it's not supersonic, is actually of the order of a Mach 0.2.3, which is pretty good going for a bird. The European peregrine, a hawk used in falconry, as you probably know, is timed at about 180 miles an hour maximum in a dive. Probably a little known fact, though, about peregrine hawks is that they have a separate skin, transparent eyelid, which comes over their eye in a dive. The normal eyelid that we have, of course, they won't be able to see. So they actually have a separate eyelid, which is transparent, to protect the eye in a dive. There are also other amazing things about the eyes in birds of prey. That will be another talk, but I could talk to you a little bit about the special instruments that there are enabling them to see at great distances, like in an eagle. But there's more versatility in an eagle with its swing wing configuration, with its variable camber wings, with its tail, which is also in a variable, can vary it just at a whim. And it also, you may have seen in the earlier video that I showed, it can also perform amazing feats when it's competing with another eagle over territory. And the dance that it performs in the air, I showed you earlier, where they actually grab talons and they swing round each other, and the only thing that can sometimes stop them is that they fall, one of them, not into a tree as they've shown on the screen, but they actually fall to their deaths. It rarely happens, but nevertheless the eagles show amazing aerodynamic ability. This is a wandering albatross which can sometimes fly distances from South Georgia to Brazil in order to get food for its young. The way the albatross will do that is with its huge wingspan. It will use the waves in order to get extra lift, because it's known that if you fly an aircraft close to the ground, you get actually what's called ground effect, where you can do the same with the sea. And if the sea is actually moving, you can actually use the waves to get extra lift. The ground effect is just simply because you're actually pushing the air down. Whenever an aircraft flies, it actually pushes the air down. And of course, if you're close to the ground, then it will push that air back up again, and it actually means that you reduce what's called the induced drag. Now, some other aspects of the aerodynamics of birds. A little known fact is that at low speed, there is another intriguing device which a bird has. We talked about high speed. Now we'll talk about low speed and indeed hovering, I'm coming to. The little known fact, which is on every bird, is that there is what's called an alula feather. Now the alula feather is a little finger which just points forward about halfway down the leading edge of a bird. Here it is on a white-tailed kite, and you can see this little feather which pushes forward. Now that's a very important feather, because what it does is it controls the airflow over the upper portion of the wing under low speed. If you don't have that, the air would just separate over the aerofoil and the bird would just drop. But with that addition, it actually puts some of the high energy air from underneath the wing into the upper portion of the wing. So the air, instead of just simply separating from the wing, is actually pushed back onto the upper surface of the wing. It basically will increase the drag, but increases the lift capacity under high angle of attack. I've only just realized in the last few weeks that a person, believe it or not, by the name Ian McIntosh, put in a patent on this device which he had seen in birds and thought that he could apply it to aircraft. He did this, I believe, in about 1907. He was actually called up in the First World War. He survived the Gallipoli campaign, came back to New Zealand, I think he was in, or it was New Zealand or Australia. He came back, I think it was to New Zealand, and when he came back, he realised that Handley Page were developing just the same thing. So he challenged them in court and said, "You're taking my patent." But Handley Page won the debate, and Handley Page actually used this device, which is not called an Alula feather like on this American kestrel, or on the red-tailed hawk there. It's actually just called a leading edge slat, but it's based on the same principle. Here it runs right along the leading edge, and you'll see it on various jetliners if you're sitting in the right place. If you look out as they're landing, the air is encouraged, as I say, to be attached to the upper wing. And indeed, the well-known disaster at Staines, when a Trident crashed on takeoff and fell out of the sky from Heathrow, was due to the pilot retracting the leading edge slats too soon. And so the lift was lost on that Trident, and it crashed in 1970s. I can remember it actually because I was aircraft spotting at the time. Now, the other thing about birds is that they can fly, some of them, such that they can hover. Actually, I didn't show you, but let me just quickly go back. The American kestrel, and indeed our kestrels here in England and Scotland and all over the British Isles, can hover. They do it by a different principle, but they flick their wings, the outer portion of their wings, and with the flared tail at the back, it's not doing it in this case, the American kestrel, but with the flared tail at the back, they could stabilize themselves and actually just hover. You often see them in the motorways and in the central reservation or at the side. They're looking for shrews, which of course they will go for as soon as they can. But a hummingbird is hovering by a very different principle. The hummingbird hovers by a figure-of-8 motion from its wings. It will hover. Let me just do it with one arm, then you can see what I'm saying. It will move the wing down, then it will turn it right over and bring it down again, even though it's bringing its upper surface down, right? So it's actually moving in a figure-of-8 motion. So it's getting lift both in the usual downward stroke and in what would have been the upstroke. So by doing that motion with the wings, it's actually performing quite a remarkable feat, which, as you well know, if you've seen them probably in hothouses here in England and Scotland, you'll perhaps have some places where you can find hummingbirds which are kept in warm conditions, and there's some beautiful photography done here where you can actually see the twisting of this blue-throated hummingbird. It effectively doesn't use any elbow. That elbow is really just about fixed, and the wings are just simply straight out, and it does this motion with the wing. Quite extraordinary birds. Now, there is also another feature about hummingbirds. They have this long beak through which there is a double-grooved tongue, which the nectar is just poured down their throats, because that's how they feed. They have to get energy extremely quickly, and the nectar is one way of getting it, and that means that they've got to go to plants which have the nectar available. They usually have a fairly long trumpet, as is the case with this flower here. And it raises quite a lot of issues as to how the hummingbird, if it did evolve, because you've got to actually make sure that the bird has a long beak with a long tongue, and a double-grooved tongue at that, in order to feed on the nectar. The tongue comes out at 5 to 6 times per second. The bird has got, therefore, to have that long beak, but supposing it didn't have the ability to hover. Well, the bird would come into the trumpet-like plant, and it would hope to get some food, and then it would go straight through the other side of the flower, destroying it probably in the process, because it hadn't yet got the ability to hover. Well, supposing it did have the ability to hover, but it didn't have the long beak. Well, it still couldn't get at the food. It's got to have both things right in order to survive and to move on into the next generation. That is a case with hummingbirds that you've got to have many features right. I'm going to show you some other features in birds which have got to be right. I mentioned a kestrel earlier. Here is a hovering kestrel, a European kestrel in that case. Now, aircraft have flaps. Now, the flaps that this TriStar from some years ago has are operated by screws, mechanical screws which actually drive the devices to actually extend them at the back of the wing. You don't need screws on a swan. Here's Swan Mark 1, flaps down, nose forward, coming into land at Swan Lakes. Tchaikovsky, well, I shall have to apologise to. But to be frank, that shows far more design, far more detail, and I would suggest to you purpose, than what we had with the Lockheed TriStar, which nobody would doubt was designed. There is no screws operating these flaps at the back here, as you can see. The flaps at the back of this, this is operated simply by muscles moving the feathers down at the back. And I would suggest to you that the aerodynamics of that is really quite amazing, because you have to say that there is the muscle arrangement plus the appropriate feathers in order to change the camber of that wing. I should remind you that feathers are not the same all over a bird. You have different types of feathers. Flight feathers are different to secondary feathers, which are different to tertiary feathers, which are different to covert feathers, which are different to tail feathers, which are different to downy feathers. All feathers that I've just named are different. The feathers must grow at the appropriate point and must be the right type of feathers. But I was really talking to you about flaps. Now, with flaps comes some penalty, which is vortices. They carry with them this penalty. You can see some more vortices here on another occasion where the flaps down are showing these vortices coming off. Now, why am I mentioning these vortices? Well, some birds actually get round the problem of these vortices. In fact, they deliberately use an extra device to get extra lift from those vortices. And the device is winglets, like on this owl, which come right at the end of the wing. All wings, not just flaps, which I showed you it for because it was easiest to show it at that particular case. A high lift device under low speed, you can, if you've got the right conditions in the atmosphere, you can actually see the vortices. You actually get those vortices off the main wing. So any wing has a trailing vortex. And yet this owl and harriers and other birds of prey will, and eagles, have these curved winglets which are placed to actually make use of that vortex. In fact, it breaks up the trailing vortex and reduces the drag from the main wing. It means that these birds are very efficient flyers. And it also means that they're barely heard because the aerodynamic noise coming from an owl in flight is extremely small. Well, there's always been the urge to fly. This chap obviously jumped to his death, and these guys were cheating because they were using a lighter than air craft, whereas at least he wasn't cheating, probably didn't live to tell the tale in that case. Now, the first people to really fly heavier than aircraft were the Wright brothers, who flew a distance roughly the length of a Boeing 747 on their first flight in 1903, but it was a controlled flight. Richard Pearce from New Zealand also tried to get an aircraft made, and he did actually fly before the Wright brothers, but his aircraft was not being controlled as the Wright brothers managed to control theirs. It is true by the end of the day they had bumped their plane. I don't think they quite wrote it off, but they did have a few bad times with it. But they did manage it, the Wright brothers. Blériot, not long after, it's 6 years later. It's quite amazing when you go through the history of flight. It only took 6 years, and the French were flying the Channel to try and reverse the Napoleonic Wars. As I mentioned to you earlier, birds, of course, have feathers. Now, I have here a feather which I should have got out earlier, but I'd just like to remind you as to what constitutes the main items of a feather. Now, we've got it on the diagram on the screen, but I want to just point out to you that this is a buzzard flight feather. The flight feathers are, of course, the primary feathers, which I indicated on the flaps on that swan earlier. Well, here are the primary feathers, which are towards the outer part of the wing. There are variations within the primary feathers. The primary feathers right on the extreme are much more curved than the ones coming further in. So you need to be aware that the primary feathers are graded depending on exactly where they are protruding. The secondary feathers, similarly, are not all exactly the same. The tertiary feathers are not the same as the covert feathers, which I'm pointing to there. And the covert feathers are not the same as downy feathers. And all these feathers that I've shown you there are not the same as tail feathers. So birds need to have the right feather growing at the right place. But there's more to it than that. On a feather, there is a remarkable bit of engineering which you can only become aware of at the small scale under the microscope. The feather shown actually in this picture is a pigeon secondary feather, but it would be true for any feather like this buzzard flight feather. You may have wondered, why do the barbs coming out of the main rachis not separate from each other easily? Of course, you can make them separate. If I do this enough, eventually I get a separation. But normally, they don't separate. Indeed, once they separated, you can make them come back together again. What causes the barbs to be attached to one another? Well, the reason is that coming from the barbs under the microscope, you will see barbules with hooks on and barbules with ridges on, coming from different sides to the main barb. So the barb, which you can see, has tiny little barbules which are different on one side of the barb than the other. That means that the barbule, which is left-handed, say, coming from one barb, meets the barbule which is right-handed coming from the next barb, because they're obviously coming in different directions. And as they cross, the hooks coming from the light-coloured blue ones here meet the ridges coming from the other side of the barb. So you've got the barb here in purple. This is a cross-section of the barb. Coming from the barb is a barbule, light-coloured blue, light blue. And coming in the other direction is a green ridged barbule, and the hooks coming from the light blue barbule grab the ridges from the green one shown in this picture. So there is a sliding motion. Well, if you've got a sliding motion, that means that you're going to actually create some friction. In order to get rid of that friction, how do you make sure that you don't fray the surface? Anything which has got two bits of material rubbing together, you're going to need something to stop that wearing. Do you know what that is? Oil. And a bird needs oil. Where does a bird get its oil from? Well, it actually gets it from the preening gland, which is right at the base of its spine. So that means that you've got another feature which has got to be right in a bird. A bird has got to be able to have the ability to turn 180 degrees. Can you do that? And now I know I'm over the hill, but I can't even turn it barely 100 degrees, just beyond 90. I can certainly not bend it 180 degrees. And once you've turned it 180 degrees, you've then got to bend your back over, and you can't do it. And yet my budgerigara is doing it every day at home. It will sleep on its perch with its head resting on its back. That's how it does it. So you see, all these things have got to be right. You've got to have the feathers in the right place. You've got to have the lightweight engineering principle of sliding joint, of the left-handed barbules being different to the right-handed barbules. It is true. Yes, we know that birds' feathers are made of keratin, which is the same as the fingernails you may still have left after the exams here at Edinburgh. And it's still the same as the hair, I know. It's actually, we'll give it to them, but it isn't quite the same keratin. But we'll assume it's the same keratin. You know, I've got a little bit of hair left over, and from my youth. And this is made of keratin, just like the keratin of the scales of an alligator or the fingernails that I've referred to. But are you going to get the scales of an alligator, or the scales, they say, of course, of a dinosaur, to change into the keratin of feathers? I would suggest to you never. You can shine as much energy as you wish onto the scales of a dinosaur, but it will never, ever change into the feather that you need, even though you might have a mutation. There will be no advantage, and there will be no way by which you can actually generate the structure that you need. You might get a frayed scale, which has been argued in the evolutionary literature, might be some advantage for this poor little creature, like a shrew or whatever it was, or velociraptor, was busy trying to run along the ground and get some advantage from getting some insects on the way. But you're never going to make the structure of a feather. In fact, Dawkins was asked this question by Jonathan Miller on the programme A History of Disbelief, I think it was 2 years ago, as to how the feather came about. And he was pressed quite hard by Jonathan Miller, in a very nice sort of way. He said, how did this actually get going? How did that, I think he used the word, that little pimple, how could the evolutionary forces, or whatever you're going to speak of, Professor Dawkins, how did it get a purchase on that little pimple to change it into a feather? Richard Dawkins thought for a while and he said, well, I suppose it's a matter of faith on my part. Well, I'd like to know what sort of faith. I would suggest to you that it's not the same faith that I have. It's a different faith. I'll come to that possibly at the end. A feather blown up here by David Menton's microscope some years ago shows this barbule, this is a barbule with hooks on, sliding over the ridge. You can't see the full extent of the ridge here, but sliding over the ridged counter barbule. And the similarity would be to Velcro, except Velcro doesn't have a sliding joint, as you know, but it's a similar type of facility. And there's the quote from Richard Dawkins that I mentioned. I suppose it is a matter of faith on my part. Just let me summarise something which is, I'm very grateful to my colleague, Dr. Surtees here, who actually gave me this slide. He may have shown it himself, actually, in one of the talks here at Edinburgh. But you remember I mentioned the Velociraptor, which is reckoned to be the precursor, and there is other dinosaur-like creatures, which I'm not going to say are necessarily every one of them land-based. It could be that they are simply, from my point of view, extinct flying creatures of some kind. But the Archaeopteryx, which I would suggest to you is actually just simply an extinct flying creature. The fact that it had hooks on its wings is no problem to a creationist belief. We know that there are birds today which still have hooks on their wings. The Hesperornis bird in South America has that, and there are other birds which have been known to have hooks. Yes, it did have teeth, and it is true that birds do not have teeth. But that doesn't prove the argument that this is a precursor to modern day birds. It just simply means that there was a creature in the past which flew, and by the way, it has fully developed flight feathers in the Solnhofen limestone quarries where the fossils are found of Archaeopteryx. It clearly shows in great detail the very highly curved flight feathers of Archaeopteryx. So there's no doubt that it was a fully developed flying creature. But what's interesting is that this, which is meant to be a precursor, is in rock, which by traditional datings, I don't accept the datings personally, but I'm just using that as a basis of argument, are in rock which is supposedly getting on for 100 million years older than Velociraptor, which is reckoned to be the early precursor. Not only that, you'll have noticed an interesting picture down here, which looks very much like bird footprints, fossilized in rock, which is meant to be 200 million years old. A slight embarrassment, surely, to the evolutionary argument that birds evolved from reptiles. It puts them in the geological column, this set of data that I've just been talking about in this region. And yet we've got bird footprints down here, supposedly 200 million years ago, when birds are meant to have evolved up here. Well, there are many things we could say of birds. I've been talking a lot about feathers. I thought you'd like to see this supposedly 25 million year old feather, which is in what we call amber, which is fossilized tree resin, which has hardened. But here you've actually got the feather itself, such that if you were to break open the amber, now you wouldn't do that unless you really were sure of what you're doing. You don't really want to lose these precious gems which have got fossils in them. But if you broke it open, you would actually pull out the feather. And you could see, because it's transparent, that the feather looks identical to a modern feather. There is no difference. Well, we need to move on. The feather, by the way, fossilized is in that tertiary rock, so it is quite late on, it is true, but it is nevertheless an embarrassment that the feathers which are supposed to have come on a lot later are essentially the same as modern feathers. Now, the Bible, which I believe in, says that fish and flying creatures were made on day 5. Many people, of course, try to make out that, well, if you sort of rejig the days a bit in creation, you might be able to work with an idea that somehow the fish and the flying creatures were coming after the reptiles, like I was just referring to. But it's a slight difficulty because in that book it says that day 6, which of course is after day 5, was when the animals, the land-based animals, were made. So that actually doesn't fit. Well, I want to move on, and I'm just going to slightly skip here if you don't mind, because I want to just move to another point which is an important one, and that is some of the other structures in birds. Birds have bones which are light. We have heavy bones, but the bones of birds are hollow. I don't know whether you realise that. The only bird which doesn't have hollow bones is the loon bird, which is a diving bird, and the birds in fact, not every bone of the loon bird is solid, but a good number of them are. Because it's a diving bird, it needs heavier bones in order to get under the water. But birds generally have a light structure. If you're going to have a light structure, then a civil engineer knows that you need to have struts going across that structure such that you guard it against breakage. For instance, with a bridge, you'll often see this 45-degree angled spars in order to give the bridge strength. Warren, in the Second World War, realized that this was a way of making wings light but still giving them strength, and so he formed what's called the Warren's Truss in aircraft. But of course that was done many years before by, I would say, the great design in birds, which already had this Warren's Truss arrangement in their bones. If you, next time you have chicken for your Sunday lunch, take one of the bones, crack them open, and you will see this light structure in a chicken's bones. So the bones of birds have to be hollow, but not only that, the muscles need to be in the right arrangement as well. Time won't permit me to go into great detail on this, but if you want to look up the structure on the web, you can easily do it, or go to any book on the anatomy of birds, and you will see that there is a major difference in the muscle arrangement between the arms of mammals, or the arms of reptiles, which are supposedly meant to be the precursors to birds, and the arms of, or the wings of, birds themselves. The bird has not just the main pectoralis major flight muscle, which is shown there, which, if you like, is similar to our main muscle, which we have pulling and pushing our arm, but it has another muscle which we do not have. If you were to do an experiment of pushing your arm up and down for about 1,000 times, I wonder whether you might get tired. I suspect you would. You try it. I mean, you could do it for a few hundred maybe. I'm doing it for a few tens and I'm going to give up soon. But I tell you why you get tired. It's because you don't have a muscle here which comes on top and pulls the arm up. You're actually doing it by the motion down here. But the bird does have it. It actually has a pulley arrangement, which has a muscle coming over the humerus, and it's called the supracoracoideus muscle. And it's a very important muscle. This is another diagram taken from the book From One Small Speck to Man. It's a lovely book written by Vij Sedera, who is a consultant surgeon, and he does a lot of interesting dissections, and he shows the detail of this arrangement in his book. So this is the muscle I'm talking about, the extra blue one here. We've got this pectoralis major muscle. We have it as well, and it's a big muscle arrangement. You know, you need it for power with your arms or whatever. That is this major muscle. But the bird, all birds have this extra muscle. Now, where is that muscle attached? Well, it's actually attached to this sternum bone, which is really the breastbone of the bird. When you have your chicken, right, you actually, if I was to turn this upside down, right, you carve down here, right? Bit sad, really, but that's what you do. But, but that breastbone is a very important breastbone that you're cutting against. As you know, it's quite a large bone. Why is it important? Because that bone has all these muscles attached, but it isn't the only thing it does. We're now moving into yet another point about birds, which is utterly extraordinary. Did you know that birds breathe in an entirely different way to both reptiles and mammals? Birds don't have a diaphragm. They actually need that sternum bone to operate in replacement of a diaphragm. And I'll show you now a little bit more detail. So, I'm sorry, I'm just moving on a bit here. The bird, all birds, have a lung which is formed of a parallel set of tubes, and the air is driven through that by that sternum bone. And I'll now show you how it works. But I need to build up the argument. This is perhaps the pinnacle, in my view, of the amazing features in birds. We could have said that the pinnacle was a feather, and to be frank, that is an amazing device in its own right. But now I'm just talking about something which has nothing to do directly with the flying, although indirectly it is to do with the flying. Because if you think about it, a bird needs to get air, oxygen, into its bloodstream very quickly. Why? Because it's using up a lot of energy. And if it was to breathe the way I'm breathing now, which is using a diaphragm and just pulling the air in and pushing it out again, that's okay for a landlubber like me. But it's no good if I'm going to be using energy at such a rate as a bird. You feel the heart of a bird, it's going, you know, the heart of a bird is really going big time because it needs the oxygen in extremely quickly. How does it get the oxygen in? Well, instead of breathing in the air through a bronchial tube and then coming to a dead stop, like we do in an inverted tree arrangement, which we call an end-flow mass exchanger, birds have a counterflow mass exchanger. Let me explain. The air comes in just the normal way, but it splits into parallel tubes, which then don't come to a dead stop, but carry on and come to another junction and go onwards. In other words, the air never stops. The oxygen comes in the air, it's given off to the blood, and I'll show you that in a moment. Then it picks up the carbon dioxide here, and it goes out the other way. The blood is coming from right to left in this diagram. The blood is constantly flowing, and the air is constantly flowing, which means that it can get much more bang for a buck in the system. It means that for a given weight of lung, it's actually getting much greater efficiency by this parallel system. Now, a bird's breathing system actually is much more complicated than that. It actually has a lot of separate air sacs where the air is stored at various points in the cycle. There are more here than I'm going to point to in the system that I'm going to speak about, because it's much more complicated than the simplification that I'm now going to give you. If you want to read the detail, look it up in the books, but there is an awful lot of complication which goes beyond what I'm going to say. But let me now give you the basics of a bird's breathing. It has the main trachea here, which we've got as well. The bird breathes in. We're going to do it together, right? So we're going to breathe in once. Right? All breathe in. And the air in, if you were a bird, would have not gone through the lung yet. It would have gone to the rear air sac, the posterior air sac, all right? You saw the names back here. I haven't quite used the same one, posterior and anterior, okay? So on this diagram, the lung is actually here, okay? But we'll stick to this diagram. Now, you want to breathe out, but don't breathe out yet. You're not allowed to. The bird, so the air's gone to the rear air sac. I hope you haven't fainted yet. But the air's just gone to the rear air sac. Now we're going to breathe out. Right? You're not doing it. Come on, you've got to breathe out. Because now, as the bird breathes out, it still hasn't breathed out that air that it's just breathed in. Do you know what it's done? It's breathed out an earlier packet of air. Because it actually it breathes in a two-stage cycle. The air now has gone through the lung I've just referred to. So it's now full of carbon dioxide, and it's breathed out, and it's gone through the lung. Okay? Now it breathes in again. It's not breathing in the packet of air that we're following, it's breathing in a new packet of air, okay? But the packet of air that we're following, at that part of the cycle, is now gone to the anterior, the front air sac. Okay, ready for coming out of the trachea. Now it breathes out again. And it now breathes out that packet of air that we've just been following. So it goes out it comes. But all the time, it's always pumping air in the same direction from the back to the front of the lung. Now, just a minute. Reptile lungs, the evolutionist says, have changed to bird lungs. By the way, I did say to you the sternum bone is involved because there's no diaphragm, and the sternum bone operates the bird lung like a set of bellows, right? And it's rather like pressing on an organ pedal, the old organs that you used to have in churches, you know, where you press the pedals. Well, it's just moving its breastbone, and it uses that as a means of decompression and compression, as it were, in the same way as we would use a diaphragm. Now, this is the problem that the evolutionist has, and this will be the same really for any system, machinery that evolution is trying to make. But this is really where it, I would say, gets worst of all for the evolutionist argument, because the evolutionist has got to say that there was a diaphragm operating lung and it changed to an avian lung. And this is what the articles actually admit. This was some years ago in Science. Recently, conventional wisdom has held that birds are direct descendants of theropod dinosaurs, basically ones which walk like birds with four limbs up here, and they say those changed to wings, okay? However, I'm translating the science speak along, in case you're not familiar with it. However, the apparently steadfast maintenance of hepatic piston diaphragmatic lung ventilation in theropods throughout the Mesozoic, in other words, the apparent lack of evidence of bird lungs in dinosaurs, right? Something which is changing. The apparent lack of that poses fundamental problems for such a relationship. The earliest stages in the derivation of the avian abdominal air sac system, right? That's the one that we've been following, from a diaphragm, one like us, ventilating ancestor, would have necessitated selection. I have no problem with that. I'm going to end on that point. So it's talking about natural selection for a diaphragmatic hernia in taxa, that's creatures, transitional between theropods and birds. And just look at this throwaway statement at the end. Such a debilitating condition would have immediately compromised the entire pulmonary, that's the air breathing, ventilatory apparatus, and seems unlikely to be of any selective advantage. In other words, it's a frank admission that there isn't any evidence, and even if you had attempted it, the poor creature wouldn't have been selected for because the creature would have been dead. That's basically what this article is saying, because a hernia would have been required to go from one stage to the other. Now, look, I'm sorry, that perhaps you say is making a statement which is going beyond what we're here to do, is it? Surely it's bringing to the fore the reality of what's involved in evolution. I know I've made a bit of a smile out of it, but isn't it a serious matter when the evidence does not match the argument? And constantly, evolution, I would suggest, is shifting its ground to try and take account of a difficulty. Evolution is based on the theory of natural selection. Now, I have no problem with natural selection. Natural selection is, if you like, the natural equivalent of artificial selection. We can breed different types of dogs by going for a particular trait and mating the two with that particular trait until you get some of these, some dogs which I don't particularly want a dog with a snout, you know, pushed in nose, like a bull terrier or whatever it is that people go for, you know, but that's what people do. Now, would you ever be able to get an Alsatian from such a beast? No. Because if you wanted to go for an Alsatian, you have to go to the original kind, which is wild, which has greater variety. The same applies to people who who breed different types of plants. I read an article recently on apples. You could get a huge variety of apples in the wild, genetically, but they're not there. They just tend to be crab apples. But when you select for that individual genetic type that you want, you can breed from a crab apple or something looking rather like that to the golden delicious and all the other types of apples you want. But in that subset of creature, or apple as I've just been referring to, you've actually got loss of information, not gain. You haven't got more than you had before, you've actually got less. And that is the problem in using, in evolutionary arguments, in using the natural selective argument. Natural selection has no creative power. It only produces that which is there already. And it's a very important point. Many people in the media say, oh, creationists don't believe in natural selection. Nonsense. We have no problems whatsoever with it. The problem is far greater for the evolutionist with natural selection than a creationist. Creationist lives quite happily with a natural selection in his thinking. Well, I've lost time and I'm going to have to finish, but I did want to show you one thing from insects. Can I just burn just a little bit more time on insects? Just one example, right? I've lost time. I've probably said too much on other things, but I did want to show you something which I thought would just interest you. I could talk to you about butterflies and I could talk to you about other things, but I'm just going to show you something on insect flight. Insect flight is fascinating. These are dragonflies. And I'll show you in a moment a dragonfly fossil. Now, the dragonfly in the central picture is being modelled by, well, it's true, this is a creature which is pinned or stuck, and they're filming it in the laboratory. It's just a crane fly in this case. But what they're doing here is they're looking at the twisting of the wing. Okay? Now, here, Jane Wang from Cornell University has done a CFD demonstration of looking at a wing end on. Can you see that it's twisting? And as it twists, it produces vortices. Now, I want you to particularly watch this trailing vortex, because I'm now going to show you a fascinating thing about dragonfly flight. Now, this is a marvelous picture by Robert Jensen from California, a person whom I know and have gone out on a field trip with recently in search of bombardier beetles, which we did find. And he takes pictures of living things. And he's got this beautiful picture here of a meadowhawk dragonfly. Now, I want you to particularly notice these wings. You can actually see that the wing is slightly curved at the front. The leading edge enables it to produce camber, and yet it's a very, very delicate wing. By the way, how could you get a fossil of a dragonfly? Think about it. I'll ask you that question in a moment, because I'm going to show you a picture of one. But while we're thinking about live dragonflies, people have done measurements on the forces on the wing. This black is the wing, right? And these red arrows are the forces acting on the wing. Now, I don't want you to look at all the detail of that. Suffice to say that you could look it up in the original article by Dickinson in 1999 in Science. But he was basically saying that if you twist the wing at the right moment, then you get more lift than if you were just to go up and down with the wing. And that's an important point. And people have only realized of late just how incredible insects are at the way they fly. Now look at this picture. This is by Robert Jensen again. This is a dragonfly in flight. I've never seen a picture like this. I was full of awe when I saw this picture. I asked him for it and he very kindly gave it to me. And what I want you to see is that the forward wings of the dragonfly are, well, let's do it here. This is the forward wing and this is the hind wing. And this is what is happening. You can't see it, of course, in the still picture entirely, but it's doing this. It's actually doing that motion. Now, it's very important that we understand the difference here. It's not doing this and neither is it doing that against them. It's actually doing that. Now, this means that it's actually controlling the vortex from the forewing, right? This is the front wing, and this is the hind wing. There is a trailing vortex coming from the front wing, the forewing. And that trailing vortex is actually being manipulated by the hind wing. If we just play this again, you will notice, and I've deliberately turned the picture around the other way so it's the same direction. Now, that bit there is the wing which is going up and down. Now, you'll see that's coming from here is this trailing vortex. Now, if I was to just show you that's right. If I now show you, this is the middle part of that video, right? Where the wing is just on its way up and it leaves this updraft of this vortex, right? So as that wing goes up and as this one is about to come down, it's actually leaving an updraft, which is very helpful to the dragonfly. And the point I'm making here is that as that wing comes down, it sees an updraft coming from the vortex from the forewing. So it's actually manipulating the vortices and using them to increase its lift. And dragonflies go 30 miles an hour. In the past, I suspect that they went an awful lot faster. Dragonflies are exactly the same in the fossil record. That's what I wanted to get over to you. That aerodynamic brilliance is exactly the same in principle. I will grant you that the dragonflies won't necessarily be exactly the same model. They won't be exactly the same as the meadowhawks and the other ones that we have today. But the one that I showed you is not different in principle to this, which is 320 million year old Carboniferous rock. People have huge problems, if they're honest, with the fossil record, because intricate damselfly and dragonfly flight is borne witness to by the scales found in these dragonflies fossils that I've just shown you. How can we say that A has changed to B over millions of years, when in fact dragonflies are the same in these rocks, supposedly 280, even 300 million years old, and they're the same in principle as the ones today? I would suggest to you that flight is a tremendous evidence of design, not of evolution. I haven't talked to you about bats, flying mammals. There are three main creatures which have the ability to fly. Birds, of course. Insects, and I've only shown you one of them, but there are many. In fact, there are far more flying creatures in insects than there are in birds, in terms of number. And, of course, the other one is mammals, flying bats. If evolution is true, then each of them must have evolved separately the ability to fly. Once would be incredible. Twice would be stunning. 3 times is scientific nonsense, in my view. There is no connection between those 3 creatures, and yet evolution insists that flight has evolved. I would repeat to you that in my scientific view, and indeed in my convictions, as you can see, I have no room at all for the evolution of flight. Flight shows by the modern flight that we have, that we can look at, that the creatures which have it are designed, and the fossil record bears testimony to the same truth, that they appear with all the functionality that creatures have today. Thank you.